Yep. Well, at Hawkins, they've set up some studios. So what I do is I record the course first, and then we set up a synchronous studio session where I basically do what you do in class. I asked everybody at the Zoom, what did I talk about? Did they understand?
Oh, that's nice. Simulation. Yeah.
Yeah, exactly. So basically, it's been okay. The benefit is that the videos now are going to be there for the class, so I get to use them. They're much better than handwritten notes.
All right, I have to do. You save them. Yeah.
Yeah, I'm saving them.
You're expert.
So, which are you doing experimental math this semester, or?
No, next semester.
Next semester, I see.
It's always in the spring.
In the spring, I see. I see. So, what class are you teaching this fall?
Combinatorics that I'm teaching, like experimental math, teaching the maple.
Oh, I see. I see. I see. I see.
I'm having fun. And multivariable calculus. Hi, Volodya. Thanks for coming.
Hi.
Hi, your advisor, right?
Exactly.
You
good to see you.
Academic co-father.
Exactly.
Hi, Tom. Thanks for coming. You probably don't remember Eddie. Eddie was.
No, I never met him.
Yeah, right. You didn't overlap. Eddie, you finished 4 years ago, 5 years ago?
Oh, man.
More, 6 years ago.
Yeah, I think it's 2013.
Wow, time goes fast.
Yeah, it goes by real fast.
Nice to meet you.
And Nathan, you remember Eddie, of course. You overlap, right?
Yeah.
We did?
Yeah, I started in 2012.
Oh, yeah, I remember Nathan. Definitely. Yeah. I remember Nathan. We did overlap. How you doing, Nathan?
Pretty good. How are you?
I'm good. I'm good.
Looking forward to your talk.
Me too. Yeah, awesome.
So Nathan is now in Buffalo.
Yep.
Oh, really?
Yeah, I'm at Canisius College.
Oh, I see. Is it snowing in Buffalo this time of year?
There is snow in the forecast for this weekend, but not like accumulating snow.
Oh, okay.
Like a couple flurries on Sunday.
Cool.
It's raining in Buffalo now.
I see. It's probably because of the weather coming down south.
Mm-hmm.
Yeah, I see. Awesome.
And of course, Eddie, you have no objection to being recorded.
No objections to being recorded.
Then you can put it in your own channel, as you sometimes do.
Yeah, I'll post. I'm due to posting them.
No, I have better thing to do. But then you talk, yeah.
Sure. Okay, so let me share screen.
Oh, hi, Adi. You have a guest of honor, Eddie, Adi Ben Israel. You must
really?
Remember him.
Oh, great. Awesome.
He's now physically in Florida, right, Adi? Today's speaker in the famous experimental mathematics seminar of Rutgers University is a former co-organizer, Professor Edinah Gnang from Johns Hopkins University, who will talk about on partial differential encoding of Boolean functions. As usual, please mute yourself, but if you have a question, you can always unmute and ask a question.
All right. Thank you very much. It's a great pleasure to give a talk at the Experimental Math Seminar, just to make sure we're on the same page. Everybody can see my slides. If you can see my slide, just holler at me.
Yes.
Okay, great. All right. And it does change when I flick, yes? Okay. All right. So first, let me give some background of what I'm going to talk about. This is a project which goes all the way back to grad school, which in some sense was started working with Dr. Z in one of the experimental math classes. I was interested in arithmetic circuit complexity, and I could tell in my discussion with Dr. Z that what he really liked was Boolean circuit complexity. So it took about 7 years to see the connection between the two. And it turns out that the glue that connects the two is partial differential equations, partial differential operators, and this is something that might be to Dr. Z's liking. So dedicated to experimental math. All right, So I'm going to be talking about partial differential encodings of Boolean functions. And then we'll segue into what I call partial differential programs. And depending on how much time we have, I'm going to sketch how to use them in isomorphism problems. All right. I invite you to ask questions at any point during the talk. Don't be scared by the 34 number. I plan to stop at slide 24 just to strictly obey the 48 minutes. So we have about 2 minutes per slide, basically. All right. Okay, so let's get started. Typically, when we think about Boolean circuits or encoding Boolean functions, we think about something like this. This is a drawing that I borrowed, so to speak, from Avi Vidgerson book, Mathematics and Computation. Very nice book. I recommend any undergrad or graduate student or faculty, for that matter, to read it. So here's a Boolean circuit which computes the parity function. So if the sum of the bits is odd, the Boolean function outputs 1, the circuit outputs 1. If the sum of bits is even, the Boolean function outputs 0. So the gates used here are the AND gates. Can you see my mouse? When I move my mouse around, can you see it? Can somebody tell me?
Yes.
Yes.
Okay, great, awesome. So this one, the wedge upside down V, it stands for the AND gates. The V stands for the OR gates, and this symbol stands for the NOT gate. So it negates whatever you input. So the AND is very easy to describe. It behaves like multiplication. If you input 2 Boolean values, it just multiplies them and outputs. The OR is slightly more interesting. It outputs 1 if either of the bits, the input bits is 1 and 0 otherwise. And all the gates we look at here are fan-in 2. So they 2 inputs and 1 output. All right. And it turns out these gates are universal. They are enough to encode any Boolean functions you want. Okay, but circuits are very hard to think about. So one way of simplifying the model is to look at formulas. So here's a formula encoding of exactly the same circuit. And the major difference between formulas and circuit, not only formulas are bigger, but formula basically don't allow you to recycle your computation. So if you look at the circuit we had here, this computation that was done in this part of the circuit is being used for this input and also being used for this input. Whereas when you look at formulas, you're really forced to duplicate the input. So X is being duplicated a certain number of times, Y is being duplicated, and sometimes part of the computation is being duplicated. So yes, you pay a price in size, but it's much easier to reason about formulas because the underlying directed acyclic graph is a tree. Okay, so most of the discussion today is going to be based on formulas, but I'm going to switch in a second gates from these AND, OR, and NOT to actually arithmetic gates, addition, multiplication, exponentiation, and I'm going to argue the two are somehow related. So before I jump in to the switch, let me pause here and inquire whether there are any questions. Any questions so far? The default way people think about Boolean circuits is AND, OR, NOT gates. They think about things like these, and they want to know what is the smallest possible circuit for encoding a Boolean function. But thinking about circuit is hard. Thinking about formula is easy. So here are examples of formulas. If there's any question, don't hesitate to unmute and raise your questions. All right, okay. But there's another way of thinking about Boolean functions. And if you're like me, you like polynomials, or you use symbolic tools like Sage, MATLAB, or Maple, you want to think about a Boolean function as a polynomial. And naive or de facto way of thinking about a Boolean function as a polynomial is just to use Lagrange interpolation over a polynomial in n variables. So the function, wherever it evaluates 1, you just plugging this Lagrange polynomial, this Lagrange factor, and it basically implements a function which is 1 where you want it to be 1 and 0 otherwise. Now, the fact that this interpolation happens to be a multilinear polynomial is actually very convenient. It turns out the polynomial here that you get by this naive Lagrange interpolation has degree 1, at most 1 in each of the variables. And because it has degree 1 in each of the variable, it actually buys us that we can read off the Boolean function directly from the coefficients. So partial differential encoding really exploits the fact that we can read off the Boolean function directly from the coefficients. So by Taylor expansion, we know that if you want to capture the coefficient of a polynomial, you just need to compute partial derivatives. And to get rid of the terms that you don't care about, you evaluate the whole thing at 0. That's what I'm saying here. So basically, what we want to do is think about evaluation of our Boolean function as applying partial derivative with an indicator vector t for a set t, which tells us which variable we're differentiating with respect to and which variable we're not differentiating with respect to. So think about one subscript t as the indicator vector for a subset of the variables, and tells us I'm interested in evaluating the Boolean function where this particular variable is assigned Boolean value 0 and some other variable is assigned the Boolean value 1. And it's not too hard to see that if you look at the congruence class modulo 2 of each of the coefficients, what you're getting is actually the Boolean function. So this connection between partial differential and interpolation construction is really what we're going to exploit to think about a different way of encoding Boolean function. And I'll get to why this should be useful. But before I jump to the other slide, let me pause here for questions. Any questions so far? Is it clear how the partial differential?
Yeah, Eddie, I have a quick question.
Yes, go ahead.
If you pretend that x and y are other x1, xn, so you can always rewrite because x or y is x plus y minus x times y. And x and y is
sure.
X and y. So why do you need this complicated construction with this? Can you just...
So you're saying, yes, that there are more easy way of describing this interpolation construction. Is that what you're saying?
Yes.
Yeah, I agree. The point here is, on purpose, I'm writing a complicated expression, and later on, I'm going to say something about the smallest possible expressions. But
okay, you have your reasons, okay.
Yeah, the only reason I do this is to say that the interpolation construction can be done by just using Lagrange interpolation, nothing sophisticated here. But you're absolutely right. I can use the sum product rule to actually express an interpolating construction. Okay, but what I wanted to emphasize on this slide is really that reading of the coefficient buys you the output of the Boolean function. All right, so now let's use this. The basic idea here is that if I want to specify a Boolean function, all I need to do, according to this model, is to specify a polynomial. I want to describe a sort of a programming language, quote unquote, where to describe your Boolean function, all you do is to specify a polynomial. Once you specify the polynomial, the coefficient of the polynomial, of course, should be carefully chosen. If I want to evaluate the function, all I do is compute these partial derivatives. And when the partial derivative is 0, it tells me that the Boolean function at that particular input is output 0. And when the partial derivative evaluation comes up to be 1, the Boolean function outputs 1. So this is a programming language that both algebraic and al-Khwarizmi would have liked. All you need to specify in this programming language is a polynomial, and then what the program to evaluate your Boolean function does is a bunch of partial derivatives. Crucially, the polynomial that you specify in the partial differential encoding has to be multilinear. So you have to come up with a multilinear polynomial that describes your Boolean function. And we just saw that if you're interpolating your Boolean function, you have such a description. Now, to give ourselves more programming flexibility, I will allow the coefficients to be roots of unity. And that's why I'm taking the power m, because the coefficients, non-vanishing coefficients, are going to be mth roots of unity. Now, the polynomial, I'm expressing it in a very special way. I want to express the polynomial as a sum of product of linear forms. And the reason I do this is because sum of product of linear form can be completely described by a 3D array. So the U is the number of product of linear forms that I want. This is very intimately connected to what they call the tensor rank. D is the degree of the polynomial, how many product of linear forms that you need, and then n is the number of variables that your Boolean function is being evaluated in. So I said the programming language here that we're using takes as input a polynomial, but what I really am saying is that it takes as input a 3D array, converts the 3D array into a polynomial, and that's what we specify. So if you give me a Boolean function, what I ask is, what is the smallest hypermatrix B can I find that underlines a polynomial which evaluates to our Boolean function? So that's the task. The task is going to be, give me a Boolean function. I go and search in my closet for the smallest possible hypermatrix B, and I want this hypermatrix to basically implement a multilinear polynomial, which evaluates to the Boolean function that you've described. And I call that the size of the partial differential encoding. So before I move on, let me pause. If there are any questions, is it clear how the polynomial is constructed and specified for the partial differential encoding? Okay. Let me assume that no answer.
Not quite. So
yes.
How do you get capital B?
So capital B is specified by the user.
Oh, okay. It's part of the input.
Yes, it's part of the input. So
how do you get to capital F?
So it turns out that B is...
This is like a encoding.
Yes, exactly. It is an encoding of my Boolean function.
Okay.
So you pick capital B such that the whole expression is a multilinear polynomial in n variables, and the coefficients basically correspond to your Boolean function. So the partial derivative evaluates to either 1 or 0, telling you whether the input is true or false. That evaluates to true or false. Does that answer your question, Dr. Z?
Yeah, thank you.
All right. Any other question? Any other question before we move on? Partial differential encoding is basically the starting point. So the idea is start with a hypermatrix, use it to encode a polynomial, and that polynomial, if the coefficients are non-vanishing coefficients or roots of unity, then you can view this as describing or encoding a Boolean function. All right. So now let's actually look at some concrete Boolean function and ask ourselves, how complex do these Boolean functions look like in this perspective? And in the middle, I'm going to answer the question, what does that have to do with the original model of gates and or and not? Okay, so as a warm-up, let me consider the easiest possible Boolean functions we can think of. And these Boolean functions are nice because we're going to turn, so to speak, a knob and make them harder and harder until we're going to argue that the corresponding description has to be hard to produce. Okay, so the easiest Boolean function we can think of are Boolean functions where I pick an arbitrary subset of n squared. N squared, you should just think about these are edges on a graph. So S really describes a graph. And what I want to know is whether some labeled graph T is a subgraph of the labeled graph S. So this Boolean function is going to say 1 if T is a subset of S and 0 otherwise. And the other Boolean function is going to be 1 if T is a superset of S and 0 otherwise. So these are the easiest Boolean functions we can think of. Okay, so what we want to do is actually come up with multilinear polynomials which actually encodes these Boolean functions. And we want the underlying description to be as small as possible. That's our goal. Is the goal clear? Goal clear up until now? What I want is I've defined the Boolean function, and now I want to tell you what multilinear polynomial does the trick, does the job for me. What multilinear polynomial tells me which Boolean function is being encoded.
So it's some kind of exclusion?
We'll see in a second. We'll see in a second. The only property that I want for P is that it has to be multilinear, and the coefficient have to be non-vanishing coefficient have to be mth root of unity. That's basically what I want. So let's go ahead and find out what these polynomials are going to look like.
Are you taking mod 2 or not?
A very good question. in the definition of PDEs at this point, I am no longer taking mod 2. It turns out if you take mod 2, you are allowing some of the non-vanishing coefficients to be congruent to 2. And what I want my partial differential encoding to be as small as possible. So I want to minimize the number of non-vanishing coefficients. So I'm setting all the coefficients that where the Boolean function evaluates to 0, I'm setting these guys to 0. So I'm no longer taking mod 2 here. Does that answer your question, Neil?
Yes.
Excellent. So as such, this P is not necessarily an interpolating polynomial for my Boolean function. And that's a point we'll come back to later. Okay, all right. So now we have this Boolean functions. Let's actually look at what the polynomial description comes out to be. So the polynomial that I want is actually, in some sense, exactly what Dr. Z taught us, the to be or not to be rule. So either you pick the variable xi or you don't pick the variable xi. And if you expand out this polynomial, the polynomial is going to have 2 to the s terms. And each of the term is exactly a subset of s. This is a canonical way of describing the power set. Now, what's convenient about this polynomial is that it's a single product of linear forms. I did not need to add many linear forms. A single one was able to do the job. And it turns out to be a linear form of degree s. And the number of variables, I took the number of variables to be 1 plus n squared. So there's a variable for each edge, and I want to allow for the constant term. That's why I have 1. This hypermatrix is optimal. You cannot come up with a polynomial whose underlying product of linear form is smaller than this. Why? Well, because the number of terms is exactly 2 to the s. And by the fundamental theorem of arithmetics, the prime factorization basically tells me that I cannot do better. I basically have 2 to the s, and each one of these is a product of binomial. As a result, the best I can do, the shortest possible description in my programming language is specified for this particular polynomial by a 1 by s by n squared by 1. So let me pause here and make sure we're clear. So I've described encoding for a Boolean function here that evaluates to 1 when t is a subset of s and 0 otherwise. And to do this, I use this partial differential encoding. And I'm saying that among all polynomials, you can use the smallest possible description is one where the underlying basically hypermatrix has tensor rank 1. So it's 1 by s by n squared plus 1. Now, if you had expanded out the polynomial, the trivial bound was 2 to the s by n squared plus 1. So we're basically saying you don't need 2 to the s terms, you just need 1. So this is the best possible scenario. This is what we want to shoot for. We want the number of product of linear forms to be as small as possible. Something similar is true for the next one, except that the product, you apply the to be or not to be rule to the complement of s. And because you want a superset of s, you need to do the product of all the variables in s. And this gives us underlying hypermatrix of size 1 by n squared plus 1. So whenever we can get the size here, the number of product of linear form to be 1, we're extremely happy. That's really what we're shooting for. And what this is telling us is that really the Boolean function that we're looking at here is very, very easy to describe. And we say that a partial differential encoding is efficient if the product of dimension is a polynomial in the number of variables. And here the number of variables is n squared because I'm thinking about every variable assigned to an edge. Any questions so far? So this is the best possible scenario we can wish for. Here's a polynomial which encodes a Boolean function. Next slides, I'm going to make the Boolean function harder to encode. Any questions so far? Don't be afraid to answer yes or no. Otherwise, I'm flying blind. Nothing.
Question for me.
Yes, question. Go ahead.
No, I said no question.
Ah, okay, great. Awesome. No question is definitely useful feedback as well. Okay, so now let's go ahead. Let's make the Boolean function harder. Remember that in the first setting, I was just testing for a labeled subset of a graph. Now I want to test for cardinality of the number of edges. I want to say the Boolean function is going to be 1 if the number of edges in S and T, the number of edges in T is smaller than the number of edges in S, and 0 otherwise. Okay, and you can do the same thing for bigger or equal. But if you know how to do it for smaller or equal, you're done. You're really done. Okay, all right. Now, this Boolean function is slightly harder. Again, the partial differential encoding is exactly the same. I want to come up with a multilinear polynomial with the property that basically the non-vanishing terms basically describe the possible candidate T's, set T's. All right. Okay, so let's go ahead and describe how we're going to go about finding this. Now, in what I'm going to describe in the subsequent slide, I want to emphasize the discussion may look more complicated than it needs to be, because here we already know that the solution is basically n squared choose size of S. However, the method that we're going to use is actually going to help us extrapolate the method for a much harder setting. The Boolean function that I really care about is the Boolean function that tests whether or not two graphs are isomorphic. Okay, so that's the Boolean function I care about. And the toolkit that I'm going to develop here is an easy version of something that I'm going to use later, depending on how much time we have.
Your hidden agenda is to prove something about the famous graph isomorphism problem. So please remind us the status of this.
That's a great question. So status of graph isomorphism is is not quite exponential. I think it's not quasi-polynomial. Okay, so the latest result on graph isomorphism is due to Babai. Babai showed that it's not quite exponential. There's some logs in the exponents. So that's the state of the art as far as graph isomorphism is concerned. I couldn't tell from the result whether we could actually build explicitly what the Boolean circuit is going to look like, but this suggests that there should be some non-exponential Boolean circuit for graph isomorphism.
Thank you.
Okay. Yes. So that's a very good point. So this is where we hope to say something about Boolean functions testing isomorphism and sub-isomorphism, but we're going to warm up with something quite easier. And depending on how we stop, I will say a few words about the much harder case. Okay, so how do we go about generically finding partial differential encoding for a Boolean function like this? What I want to do is basically build upon Polyas enumeration theorem. So Polyas enumeration idea is to look at something that he called the cycle index, a construction for enumerating orbits. But what I really want to do here, because I care about the partial differential encoding, I don't just want to enumerate orbits, I actually want to list representatives. I want a mechanism that is going to give me a list of representatives for each of the orbits. And I'm picking right now the easiest group you can think of. This is the complete group on the symmetric group on the edges. Later on, we'll look at a subgroup that's much more interesting. So how does it proceed? We proceed by coming up with some variant of the cycle index. For us, this is a polynomial, this is a vector, which basically depicts for us the trail of the orbits of the symmetric group acting on vertices. So you pick vertex I, and you let sigma act on vertex I, and every time you track which permutation acted on vertex I. So this part here, the lex, is our way of keeping a record of where the permutation sigma took my particular vertex I, and I'm storing this information. So the orbital z and entry I is storing every place that I went when acted by some permutation sigma, and I keep all the representative. So this seems like overkill for this problem, but I will do exactly the same thing later on when the symmetric group will act on the vertices and induce a subgroup on the edges. All right, that's the first ingredient. The second ingredient is the search and replace feature. And this is quite useful. So what I say is I go to the original polynomial, the simplest one that we define, the one that only tests for subsets, labeled subsets. And what I do is I plug into that polynomial my orbital vector. Instead of plugging in the original variables x, I'm plugging in my orbital vector. And here, what the modular is doing is basically performing search and replace. So what I'm saying here is that the canonical representative of the congruence class, which means when you compute the division, the canonical representative of the congruence class is the polynomial, which only depends on entries of y's and no longer depends on entries of z. And if you played around with polynomials, what really I'm doing is just substituting everywhere where I see a product of zi having the same permutation, I'm replacing it by a product of j's, where I replace the lexicographic mapping of the permutation by actually the lexicographic mapping of the set. So I'm throwing away information about the permutation and replacing it by the set. And what this allows me to see, it allows me to actually look at what's happening, which are the graph which result from the action of the symmetric group. So let me make this explicit. Here's basically what happens. So after I do my search and replace, what happens is I get a polynomial in y, and the polynomial in y is actually telling me how many times an orbit occur. These are the number of times the same orbit occur. And here the exponent basically has to do with the automorphism group. This is the number of permutations which did not change my monomial. So I call this the orbit list generating polynomial. And this is basically the same idea as Polyas enumeration technique. Now, what this allows me to do is once I have this polynomial, I can use this polynomial to get my so-called PDE. If I can turn this into a multilinear polynomial, I have a home run. That allows me to get the PDE. So let me do just that. So in the next step, I do exactly that. So if you notice, it's the same search and replace procedure that I applied before. The only difference is that in the previous expression, I've replaced this subgraph by a graph which actually uses as index the name of the graph itself. Whereas in this encoding, I'm replacing a subgraph by a 2x2 matrix. And these 2x2 matrices have been specially chosen because they basically enable me to turn multiplication into additions. If you multiply these matrices, what really happens is that you're adding these guys. And addition is exactly what I want because I want a polynomial which is multilinear in my variables. I don't want any exponents. I basically wanted to get rid of these exponents. This exponent and this factor, I wanted to get rid of it. And to do that, I basically I did a search and replace, replacing it by this matrix. This factor is going to die out because it cancels out. And the exponent is also going to die out because of the triangular structure of the matrix. So this basically gives me an explicit expression for my polynomial. Now, this expression is not efficient. In other words, by no stretch of the imagination can I argue that this is easy to do. I had to do, in the worst case, n square factorial substitutions. However, I'm arguing that this gives me an explicit expression for the polynomial that I care about, and I want to start reasoning about the expression that I have.
It's lost. So
yes.
You want to formulate when two graphs are isomorphic?
No, at this point, I want a Boolean function that tests whether two graphs have the same number of edges or the number of edges in the second graph is smaller than the number of edges that I have. Basically, I want to implement majority.
Okay.
So the Boolean function that I want
to actually count them, then do this complicated thing.
Sorry, come again.
It's easier just to count them, then do this very complicated expressions.
So at the end of the day, what I want to obtain is the polynomial that I have here. I want to describe an expression for the polynomial. And I totally agree with you that if the goal is just to obtain this polynomial, I don't need this orbit listing mechanism. But in a second, I'm going to show that this orbit listing mechanism doesn't just give me an expression for that polynomial, it also gives me an expression for problems much harder, such as graph isomorphism.
So it's building up to other things.
Yes, exactly. So the idea really is to build up from subsets to cardinality to isomorphism. That's really the goal here. Otherwise, it's very easy to describe a polynomial whose support basically tests for the cardinality of the sets.
Thank you.
Okay, all right. Okay, all right. So, so this substitution basically outputs our polynomial. Now, the bad news is that if we expand the polynomial, we're sort of in trouble. The underlying hypermatrix, we no longer have one. We really wanted to have one, but instead we have this sum of binomial coefficient. This just comes from the fact that the support of the polynomial is all the monomials which are multilinear and have less than s variables in them. So this is the trivial bound. S is the degree, the maximum degree of any product of linear form is s, and the number of variables is n squared because we have n squared edges. All right, so this is upsetting because these are Boolean functions that we know are easy to describe. And what's more, thanks to a result of Ashtai, Komlosh, and Zemeredi, we actually know that the circuits for these Boolean functions are small. So we really expect that the partial differential encoding should be small because we know that these are actually small monotone circuits. So if I can't get rid of this sum of binomial coefficients, then everything is dead in the water. The partial differential encoding are completely worthless and not worth our attention. So let's actually rescue the model. It turns out that if we exploit the fact that our Boolean functions have variables which are basically, I can always replace xi squared by si, it actually broadens our model quite a bit. And I'm saying, instead of specifying the multilinear polynomial directly, the way I was doing it before, I'm going to specify the multilinear polynomial implicitly up to congruence by these relations. So I'm going to say, well, maybe it's too much effort to actually express the multilinear polynomial in its expanded form. Let me instead express the multilinear polynomial up to congruence modulo these relations, which are very natural relations in the Boolean setting. So if you give me a polynomial and you want to specify a PDE, your polynomial that you describe has to be multilinear, period. However, if you're describing a partial differential program, you're allowed to specify the multilinear polynomial implicitly. You're allowed to say, well, I'm giving you a polynomial that is not multilinear, but once you apply the reductions to it, you're going to get the polynomial you want. Now, this is important because it turns out that this is going to tie us back to the circuit encoding. Okay, so before I jump onto the next slide, let me just pause here and make sure we understand the difference between partial differential encoding and partial differential programs. In a partial differential encoding, the polynomial here has to be multilinear. No modulo can be invoked. In the partial differential program, you can describe a non-multilinear polynomial provided that it's congruent to the correct multilinear polynomial. Any questions about the difference between PDPs and PDEs? No questions? All right. Okay, so let's go ahead. So what do PDPs buy us? Well, it turns out that PDPs are going to buy us connections with our original circuits. If we look at the conversions that was initially prescribed by Boole, it basically tells us that we can convert our circuits into algebraic expressions and vice versa. And more specifically, what it tells us is that I can actually convert very specific circuits into the corresponding algebraic expression. This is a piece of the circuit that we saw before. And I'm saying that the algebraic expression that I'm looking at for this circuit is the one here. And this expression for qxy is actually a partial differential program. Why? The polynomial here is not multilinear, but it is congruent to a multilinear polynomial, which is related to a partial differential program. And what this tells us is that if we have a Boolean formula, what you're actually describing is a partial differential program. In particular, what we just saw is that this Boolean function that we have here, this implicit description, gives us a very short partial differential program for that Boolean function of size 1 by 2 by 3. Now, this is interesting because, and here I'm bringing back what the question that Neil raised at the beginning of the talk. At this point, it's very important to mod by 2. I'm modding by 2 because I want to relate this construction to the actual interpolating polynomial, and the coefficient can be different by congruence classes modulo 2. Okay, so in the beginning, I said we start with circuits. Then for a second, I forgot about circuit and focused on these multilinear polynomials. But I'm saying the multilinear polynomials are sometimes hard to describe. If you look at partial differential program, well, you not only do you get circuits, but you get descriptions that are typically much smaller. And here we're just exploiting the fact that we have an implicit description of the polynomial that we care about. Okay, all right. What's an example showing us what you gain? The first thing you want to realize is that small Boolean formulas automatically imply the existence of small PDPs. And PDPs tend to be smaller than the corresponding PDEs. To make the case in point, let me consider an example. So here's a Boolean function where I specified the truth table. If I wanted to specify a PDE for this Boolean function, here's what the polynomial is going to look like. So this polynomial is what I get. Because it has a sum of two terms which are algebraically independent, I cannot express this polynomial using a hypermatrix which is smaller than a 2 by 2 by 3. 2 by 2 by 3 is really the best I can do if I want the expression to come out to be multilinear. However, if I'm allowed to express the polynomial implicitly, I can actually encode the same Boolean function with a 1 by 2 by 3. And basically, I've saved 1. The price I pay is that the expressions for the entries of B are now very complicated. They're no longer 1s and 0. They can actually be some very nasty radical expressions. But as far as I'm concerned, the size of a PDP is just determined by the size of these. And we just saw that circuits also describe PDPs. So formulas in particular describe PDPs. So PDPs are going to be our proxy for establishing whether small circuits exist or not. Okay, all right. So now we can go back to our problem, the so-called function that we cared about, the function that tests whether the cardinality of the edge sets is smaller for your input t. And it turns out that we saw when you wanted a PDE, there was no easy way to actually do better than this sum of binomial coefficients, this is basically exponential. However, when you're looking for a PDE, PDP, you can actually get this thing to be 1. And the reason we're able to get rid of all of these is because the Boolean function in question is actually symmetric with respect to permutation of the variables. And because it's symmetric, I can use Newton's identities to actually turn it into a univariate polynomial in the sum of the variables. So basically, that's what you do to get rid of these. So symmetry here played a crucial role in exhibiting the fact that there are very small PDPs for the Boolean function. And because there are small PDPs for the Boolean function, this basically serves as a proxy to establish that there must be small Boolean circuits for these functions, because this is the smallest we can actually hope for. Okay, so PDPs is really what we're going to focus on, because PDEs tend to be hard to hard to get a handle of. All right, good. I'm seeing, I should have said bad because we're getting slow on time. Now let's actually consider a problem that might actually be relevant to combinatorics. Okay. So where are examples where PDPs occurred in the past? Are these new? Am I suggesting PDPs for the first time, or these occurred somewhere in the literature? It turns out that the first PDP goes all the way back to Cauchy. Cauchy's treatise on the determinant. And let's actually see how this works. Suppose I wanted a Boolean function which evaluates to 1 if the input graph is a spanning union of disjoint directed cycles and 0 otherwise. Now, it turns out that if you want such a Boolean function, all you need to do is use the determinant of the matrix A. So our variables now are the entries, and you should think about the input to your Boolean function as the adjacency matrix. So I plug in an adjacency matrix, you evaluate this PDE, and then it tells you 1 if your graph is a spanning union of disjoint cycles and 0 otherwise. Okay, all right. So now let's actually see. This PDE as is actually very bad. Naively, we don't know how to get better than n factorial by n squared. It's a horrible PDE if you think about it because of the n factorial. However, if you invoke the trick that Cauchy used to relate the determinant of every matrix to the van der Monde determinant, you can actually express a PDP for the determinant. And the PDP uses slightly different relations. I'm not here modding by the Boolean congruence relations. I'm modding by a slightly different set of congruence relations. And this gives us a PDP which is actually quite small. And I've tried, this is Cauchy's trick, basically for defining the determinant of n by n matrices. And I've tried very, very hard to do better and failed. And I've come to conjecture that it is not possible to come up with a PDP whose size is smaller than, if you do the product of the sizes, n cubed plus n squared, basically. There are several polynomials you can come up with. There are several PDPs that actually achieve this bound, but none actually comes out to be better. So I think given where we are in time, let me stop here and say.
And what about the permanent? Is something analogous?
Very good. That's a very good question. So now let me, because Dr. Z pointed out this question, this actually allows me to say a word about the permanent versus determinant. Now, this PDP, as I said, is very old. And the same paper where Cauchy actually described this construction, how it relates to the determinant, he also introduces the permanent. Now, here's what's actually interesting. It turns out if you ask somebody, I give you a PDP, he was going to say, well, I don't really care about the program description of your polynomial. I actually want to evaluate the Boolean function. And to evaluate the Boolean function, unfortunately, there seems to be no way to avoid expanding. And expanding is really what hurts you. If you have to expand this polynomial, you're really in trouble because you're going to basically produce even more than n factorial term. Now, what actually surprising here is that the question of separating PDPs versus PDE captures the permanent versus determinant question, in the sense that there exists a single polynomial for a PDP, for which when you expand the polynomial before doing your congruence relations, you actually get the permanent. And when you keep the polynomial in factored form and do your search and replace, you actually get the determinant, which basically suggests that the separation between the permanent and determinant is much harder than we expect, because it suggests that there are no way to bypass expanding polynomials to get the permanent. And expanding polynomials, I must say, is a very powerful operation, because if you can expand a 3-sat, you can determine whether the 3-sat is satisfiable or not. So really the question of PDP versus PDE is asking what is the smallest amount of polynomial expansion can we get away with and still get a hold of evaluations of our Boolean function. So unfortunately, I ran out of time. If I had more time or next time, I'll be glad to give the second part, which actually discusses the more difficult Boolean functions, which are the ones having to do with isomorphism and sub-isomorphism. But it's a good place to stop here, and I'll be glad to take more questions.
Let's thank Eddie first. Are there any questions from the audience? So I have a quick question.
Yes.
So what's your hidden agenda? I know that you always want to prove some major open problems, but you probably were too modest to describe it. So this approach could give some insight, but
okay, this is being recorded, so I have to be very careful with what I say. Basically, there are two hidden agendas here. The first is really understanding how partial differential operators in other disciplines are very powerful enough to model everything that they care about. In physics, partial differential operators and partial differential equation seems to capture everything that they're doing. Whereas a computer scientist would have expected that physics would have been done just discussing Turing machine. Why aren't physicists modeling the world and the weather in terms of Turing machine? Basically, the argument here is partial differential encoding capture Turing machine and far beyond. That's first agenda. Second, more interesting agenda is we want proxies. We want to ask ourselves, how can we cheat on Boolean circuit? How can we generalize Boolean circuit so as to actually establish some lower bounds? And the interesting observation that partial differential programs actually tell us is that if you work with a programming language that uses polynomials, then the Polynomial enumeration theorem actually gives you a way of lower bounding circuits. So you can actually, if you modify Polyas enumeration theorem into a Polyas listing theorem, so you need some search and replace, then what you actually get is an explicit algorithm for lower bounding size of circuits. Now, it is not going to be an efficient procedure. However, it allows you to reason about how small you can get the circuits to be. So you cannot hope to use Polyas listing to actually find the optimal circuits. However, you can actually use the argument to say, well, from what I know from the generating functions in Polyas, I can tell you that you cannot hope that a circuit would be smaller than this and this size. So that's the long-term goal of PDPs. Did I answer your question, Dr. Z?
Yeah, so it's an approach to tackling the extremely difficult problem of lower bounds.
Yes, it's an approach to getting lower bound by modifying Boolean circuits into things that are much easier to analyze. PDPs are easier to analyze than or not gates, basically, is what I'm saying.
Makes sense. Looks very promising. Are there other questions? If not, let's thank Eddie again. Thanks so much.
Thank you.
Thank you for coming. Thank you.
All right, everyone. We will. Thanks for coming again. We will see you back here next week at the same time.
Thank you, Robert, for organizing it. Thank you. Bye-bye, everybody. Thank you.
All right. Bye-bye.